Hello friends, in the previous class we have studied about designing a filter using bilinear transformation. In this video we will be discussing another method to design a digital filter known as impulse invariant transformation method. The question given is design a low pass filter which is required to meet the following specification. 20 log h of j omega is omega when omega is equal to 0.2 pi is greater than minus 1.9328 dB. 20 log h of omega when omega is equal to 0.6 pi is less than minus 13.9794 dB. This is Kp and this is omega p, Ks and omega s. It has maximally flat frequency response. Find h of z to meet the specification using impulse invariant transformation. When the question given is maximally flat frequency response, we have to design a Butterworth filter. The steps required to design a Butterworth filter remain same up till obtaining the transfer function h of s. We have Kp is equal to minus 1.9328 dB, omega p is equal to 0.2 pi, Ks is equal to minus 13.9794 dB, or omega s is equal to 0.6 pi. We know that t is equal to 1 second. The pre-warping equation omega p is equal to wp by t when wp by t is equal to 0.2 pi and omega s is equal to 0.6 pi radian per second. N is equal to log of 10 raised to minus kp by 10 minus 1 divided by 10 raised to minus ks by 10 minus 1 whole divided by 2 log omega p by omega s. Substituting the values of omega p, omega s, kp and ks, we get n is equal to 1.7096. Rounding it off to the next integer, we get n is equal to 2. For n is equal to 2, we know the Butterworth function Bn of s is equal to s square plus root 2s plus 1. Taking the inverse of the Butterworth polynomial, we get transfer function h2 of s is equal to 1 divided by s square plus root 2s plus 1. After obtaining the transfer function h2 of s, we have to find the cutoff frequency omega c given by omega p divided by 10 raised to minus kp by 10 minus 1 whole raised to 1 by 2n. Omega p is 0.2 pi divided by 10 raised to minus kp by 10 is minus 1 is 0.56056 whole power 1 by 2n. N is 2, 2 to the 4, which gives the answer as 0.726146 radian per second. This is the cutoff frequency omega c. Since we are asked to design a low pass filter, we have to apply low pass to low pass transformation. For low pass to low pass transformation, we have to substitute s as s by omega c, where omega c is 0.726146. Applying the same, we get transfer function h2 of s is equal to 1 divided by 1.896528 s square plus 1.94956 s plus 1. We have to keep the coefficient of the highest order as 1, hence divide numerator and denominator by 1.896528. After dividing numerator and denominator, we get h2 of s is equal to 0.52728 divided by s square plus 1.02690 s plus 0.52728. To apply impulse invariance technique, the denominator should be in the form of s plus a whole square plus b square, which is equal to s square plus 2as plus a square plus b square. Comparing the denominator and this equation, we get 2as is equal to 1.02690 s and a square plus b square is equal to 0.52728. Equating the same, we get the value of a is equal to 0.512929 and a square plus b square is equal to this 0.52728. We know the value of a, hence b square is equal to under root of 0.52728 minus a value square. Hence b is equal to 0.51398. Keeping the denominator in the form of s plus a whole square plus b square, we obtain h2 of s is equal to 0.52728 divided by a value is 0.512929 s plus a whole square plus b square. B is 0.51398 square. Hence, to apply the impulse invariance technique at time t is equal to 1 second, we have b divided by s plus a whole square plus b square is equal to e raised to minus at sin bt z inverse divided by 1 minus 2 e power minus at cos bt z inverse plus e power minus 2at z power minus 2. Substituting the value of a as 0.512929 and b as 0.52635. After solving the equation, we get h of z is equal to 0.301 z inverse divided by 1 minus 1.0433 z inverse plus 0.3585 z power minus 2. Substituting z is equal to e power j omega, we get h2 of omega is equal to 0.301 e power minus j omega. Since it is minus 1, we take e power minus j omega divided by 1 minus 1.0433 e power minus j omega is plus 0.3585 e power minus 2 j omega. Since it is z power minus 2 is attached here, e power minus 2 j omega. We know that e power j omega is equal to cos omega plus j sin omega. Substituting the formula here, we obtained h2 of omega as 0.301 into this e power minus j omega, and similarly in the denominator. Evaluating this h2 of omega when omega is equal to 0.2 pi, taking the 20 log of that function, we get 20 log h2 of omega at omega p is equal to 0.2 as minus 2.0535 dB, and evaluating the same h2 of omega when omega p is equal to 0.6 pi, we get 20 log h2 of omega is equal to minus 12.9 dB. This we have to obtain this both as given in the question. In the question it is given as kp is equal to minus 1.9 dB. Hence we obtain the nearest value, and here ks is given as minus 13 dB in the question. We obtain minus 12.9 dB.